This is called a non-redundant mask, and it's non-redundant because it has more than one hole in it. It's going to be going on the James Webb Space Telescope, which is the successor to the Hubble Space Telescope. It's due to be launched in 2014. And it's going to be part of a system that enables us to see objects that are fairly dim next to things that are extremely bright. And that's the whole idea behind this instrument.
When the James Webb Space Telescope launches, the mirror of this telescope that's going to be pointed at all of these objects that we're interested in is going to unfold. And it will end up being about the size of the blue wall behind me. And what that's going to do is it's going to catch light from the things that we're interested in and focus it onto some instruments, onto a camera. And what we're going to do is we're going to put this mask in front of the camera. And what that lets us do is it lets us see dim things next to very bright things. If we didn't have that mask there, we'd just see a very bright thing and we wouldn't be able to see detail around it. If we put this mask in the way, we get to see some of the detail around the very bright thing, and that's what we want to do.
This type of technique, taking light from a bunch of different light paths like this, that's what this does. Basically, it takes all the light coming into the telescope, but it actually only samples these 7 points. That idea has been used in radio astronomy for about 50 years, and in radio astronomy it's called interferometry. And some of our colleagues at the Museum of Natural History, American Museum of Natural History, said, you know what, you could do this with light that we can see with our eyes, visible light. And we were talking to them, and they said, you know, this would be a great way to be able to see planets around stars, which are dim sources next to bright sources. So planets are not so bright, and stars are extremely bright. You could take the same technique and apply it to sources outside our galaxy. So these extremely bright active galactic nuclei, these extremely bright supermassive black holes, and then you could see the galaxy around it. You could see what's going on to get the mass into the black hole and exactly how it's being swallowed, which is really interesting for astronomy and also for physics.
So our collaboration involves people from the American Museum of Natural History, UCLA, Princeton, Cornell, University of Sydney, and myself and Saavik here at BMCC, and also Space Telescope Science Institute. And so this collaboration, what we did was we came together, and on the basis of the white paper, we basically said, look, let's apply to NASA for a technology development award. And NASA reviewed our project, and they thought it was a very good idea. And they awarded us, I think, $1.5 million. And so myself and Saavik are the extragalactic side of that project. So most of the money is going into technical development, software development, figuring out what would happen if you used this on particular instruments looking for planets around stars. Myself and Saavik are interested in figuring out what would happen if you used this on a space telescope looking at faint things around supermassive black holes. So basically, we're the part of the collaboration that's looking at things outside our galaxy. The bulk of people in the collaboration are instrumentalists and trying to figure out what we would see if we looked for planets around stars.
What we're planning on doing with the successor to the Hubble is we're going to be looking at a number of different galaxies. We're going to be looking at the regions close to the black hole that lives at the centers of these galaxies, and we're going to try and understand how material is getting from the galaxy into the black hole, because we think that we have an idea of how black holes have to swallow matter, actually right at the very closest bits, but we don't really understand how the black hole interacts with the galaxy. We know that black holes know about their galaxies from other studies. We know that they tend to live in particular size black holes, live in particular size galaxies. We also know that the galaxies tend to know about their black holes. Particular types of galaxies host active black holes and non-active black holes. So we know that they're talking to each other, but we don't really know how. And we would like to be able to see the point where they are talking to each other so that we can try and understand what's actually going on. And so this summer we're planning on drawing up a list of targets that Hubble's successor will be looking at with this instrument for us. We'll be looking for is star formation going on.
The significance of what we're doing is that we can see details with this that we couldn't otherwise see. Whatever it is you're looking for, whether it's planets around distant stars or disrupted stars spiraling in their death throes into a black hole, if you want to see any of that, you're going to have to block out the main central light source and look for the faint things around it, and this is the way you do it. So what I want to do is I want to see further and deeper with this thing than we've managed to do before. So get as close as you can to the action.